In this lesson, we're going to look at geometric sequences and series. Now, last time we looked at arithmetic, which means we're adding or subtracting to go to our next term. We have a common difference. With geometric, the change is we are going to be multiplying or dividing to get to the next term in the sequence. But everything else we can think of in the same way. So we still have a sequence is just a list of numbers. Geometric just tells us what the pattern or what type of pattern we have, that we multiply or divide to get to the next number. We still have series, which is going to be the sum of all the values in that sequence. But the new thing that we have for geometric sequences is something called an infinite geometric sequence. Now, if you think, or infinite geometric series rather. So infinite, just like we've talked about before, infinity is the concept that values get bigger and bigger and bigger going towards infinity. Well, if we have a geometric sequence, there's two things that can happen. So either we have a sequence that we multiply by a number and everything gets smaller and smaller and smaller and smaller, eventually getting down towards zero. So for example, we have, if we started with like 4 and then we divide by 2 in each step. So divide by 2, divide by another 2, divide by 2, and our fractions keep getting smaller and smaller and smaller, and eventually we're going to just have a teeny tiny fraction that, for all intents and purposes, will eventually get down to 0 or very close to 0. But if we go the other direction, if we multiply by a larger number instead, so let's say we started with that 4, and then we keep multiplying by 2. So times 2 is 8, times 2 is 16. What's happening with our values? We keep getting bigger and bigger and bigger. And so if that just keeps continuing, we're eventually going to be getting, excuse me, need to put my mic back on. Eventually, we're going to be getting to very, very large numbers. And so if we try to find the sum of that series, we can't actually do that. Our series isn't going to get to a point where that value, as we get to really, really large values, we're not going to be getting down to 0 like we were with the first sequence, where we were, getting smaller and smaller and smaller as we went on. Bigger and bigger values means the sum of that whole sequence eventually is going to go to infinity. We can't really find that number value for it. So that's why when we're looking at our formulas, we've got this new formula down at the end, S sub infinity, with a little infinity symbol, just meaning that the sequence could go to, closer and closer to 0, which means we can actually find a value, hence we have the equation. Or if the value that we're multiplying by is bigger than 1, then we can't actually find the sum. And you'll notice in the formulas too, we also, instead of the D for the common difference, we have R for the common ratio. In other words, the number that we're going to be multiplying by at each step to get the next number in the sequence. So just like before, let's look at several different examples and see how we can apply these. So first two terms, or find the next two terms in the sequence. So first, let's establish the pattern. What do we have to multiply by to get to the next number? So what I'm going to do is I'm going to take 20 and divide them by 8 to see, well, what was that extra multiplier in there? And so 20 divided by 8, I am going to get a fraction out of this. I get actually 2.5. So test it out. 8 times 2.5, well, that's going to give a larger number. That's going to get us to 20. 20 times 2.5 gives us 50. And so next one, 50 times 2.5, that's going to give us 125. And then 125 times 2.5, that will give us 312.5. So those are our next two terms, 125 and 312.5. All right, number 2, though, you'll notice the values are decreasing. So that means we're going to be multiplying by a number that's smaller than 1 or dividing. And so what can I divide 81 by to turn it into 27? What can I divide 27 by to turn it into 9? If I look at those second two terms, I can see, well, 27 divided by 3 gives us 9. Test that out. Well, 81 divided by 3 gives you 27. So next two terms, well, 9 divided by 3 would give you 3. 3 divided by 3 would give you 1. And so actually, let's note what we figured out on these. So in number 1, we figured out our common ratio was 2.5. In number 2, we found out or decided our common ratio was actually 1/3 or 0.3, repeating I tend to write it as if it's a terminating decimal, go for it, use it. If it's not, but you have a repeating decimal, probably easier to express it as a fraction so you don't accidentally kind of truncate that number and get incorrect values when you're trying to calculate these out. Alrighty, number 3. So again, let's see here. -3, what do I multiply to make a +6? Well, I've got a sign change on here. So, well, if it was just 3 times 2, that would make 6. So what about a -2? So if I have r equals -2, does that work for the next one? So 6 times -2 gives me -12. So that's my common ratio. So there we go. That means my next two terms, well, -12 times -2 would give me a +24. And then +24 times a -2 would be -48. Alrighty, 4 and 5, find the first 5 terms of the sequence like we did with arithmetic. So again, they're giving us our a sub 1 and our common ratio. So we could do this with the formula that we have at the top of the page, which was a sub n equals a sub 1 times r raised to the n minus 1. How many times we're multiplying that r? Again, an exponent just tells you how many times you're multiplying that same value over and over again. So we could find a sub 2, our second term. Our a sub 1 was 2. Our common ratio was 5. And we're going to raise that to the n minus 1, so 2 minus 1. In other words, 2 times 5 raised to the first power, or just 5, and that's 10. But again, you don't have to go through that formula. If we just have a few values we have to find, let's just multiply through by our common ratio. So times 5, so a sub 3 would be 10 times 5, which would give us 50. A sub 4, that's 50 times 5, so that's going to give us 250. And then a sub 5, again, 250 times 5, that would give us 1250. Alrighty, same thing, number 5, a sub 1 is 768. Our common ratio r is -1/2. So if we just had a plain 1/2, what would happen to our overall values? Well, they would just get smaller and smaller and smaller. They would get halved at each step. But with the negative, we're also going to be flip-flopping on our negative signs as well. So again, rather than doing the whole formula, let's just multiply through by that -1/2. So that means a sub 2 is going to be 768 times -1/2. In other words, -384. So our absolute value got smaller. Actually, the whole thing got smaller, but we did flip the sign on it. Okay, so same thing, -384 times a -1/2. So that's going to come out to a +192. So this one, again, if we have the 1/2, yeah, our numbers are kind of shrinking in closer and closer to 0, but we are flip-flopping positive, negative, positive, negative. So we have this kind of oscillating pattern on here. So a sub 4, again, multiply 192 times -1/2, it'll be negative, and then 96. And then our fifth term, again, we flip back over to positive. Half of 96 is 48. Alrighty. So again, what if we're not just straight out calculating our values? What if we need to go a little bit further than we want to do, brute force? So again, we go back to our formula. So we know that a sub 1 is 1/49. Our common ratio is 7, so we're going to keep multiplying by 7. And this one's giving us n equals 6, so that means we want to find the 6th term. So I want my formula a sub n, and I'm just going to copy my formula straight out from what I have. So a sub 1 times r raised to the n minus 1. So let's just fill it in. So a sub 6 equals 1/49 times 7 raised to the n minus 1. 6 minus 1 is 5. So my suggestion would be go ahead and find the power first. Again, the 5 exponent is only getting applied to the 7, not to the 1/49. So 7 raised to the 5th power is actually a pretty large number, 16,807. And then when we multiply those out, we actually get 343. So that's a sub 6. Alrighty. So think about that for a second. Your R, your common ratio was 7. So you're multiplying by a number bigger than 7. So your values in your sequence are going to keep getting bigger and bigger and bigger as you go on. Okay, number 7. They gave us the same info, but now our common ratio is 1/5. So what should happen to our values? Yeah, smaller than 1. So that means that our values are going to get smaller and smaller and smaller as we go on. So let's see. We're looking for which term? Yep, n equals 10, so the 10th term. So a sub 1 is 78,125 times 1/5 raised to the n minus 1, or raised to the 9th power. And again, the 9th power only goes to the 1/5. So I would calculate that first. If you are going to type this into your calculator as is, absolutely make sure you're being very liberal with your parentheses. Make sure that you're telling your calculator or Desmos the exact order of operations that you want to use. So 1/5 raised to the 9th power is actually going to get you this funky decimal, 5.12 e to the negative 7. So that really just means we're going 7 places of moving over our decimal point. So we have 512, but move it over. So 1, 2, 3, 4, 5, 6, 7, and all these leading zeros. If you're using a TI calculator, though, once you calculate that, just hit multiply by 78125, and it'll automatically feed that in. You don't have to retype that. And that should come out to a small number, but not as small as you would think, of 0.04. And again, if you're dividing by 5 each time over and over and over again, your numbers are going to get pretty small pretty quick. Alrighty, number 8 and number 9, again, they're just tweaking the info, but it's the same kind of application. So we're going to find a sub 7 if a to the n is 12 times 1/2 raised to the n minus 1. So what's our n value going to be? Well, if a to the 7, that means we're looking for the 7th term. So n equals 7. And since they gave us the formula, we just have to plug in. So a to the 7 equals 12 times 1/2 raised to the 7 minus 1, or 6. So 1/2 raised to the 6th power is 0.015625. Not as long of a decimal, not so many zeros, so that's why you're not getting that times e to the whatever negative value. It doesn't have to resort to scientific notation on you. And then multiplying that out, we should get 0.1875. Alrighty, number 9, so find a sub 6 for the sequence. So they didn't tell us anything other than we have our a sub 1. But what do we have to do to get to the next term? What's our common ratio? 1 times what equals 5? Well, that's 5. So does that work with 5 to 25? Yep, so r equals 5. So a sub 6 equals 1 times 5 raised to the n minus 1, aka 1 times 5 raised to the 5th power. So 5 raised to the 5th power, large value, that's going to be 3,125. And the whole thing gets multiplied up by the 1 out in front. So that's all there is to it. Alrighty, next set. So just like with arithmetic, we can find geometric means. So that is our next type of problem. Which means we're looking for our missing terms in the middle of a sequence if we're given the first term and the last term. So again, same thing, we need to figure out, well, how many steps do I take and what's the ratio that I'm going to use to get there? Now we do this a little bit differently. We're actually going to use our formula that tells us what our terms are. So for reference, we're going to use our a sub n formula, which is a to the 1 r n minus 1. Because I know now, I know my first term, 1 for number 10, that's 1 over 24. I know my last term, which in this case, that's my 5th term, so a to the 5 is 54, which means I can also know that n equals 1. And if I plug it into the formula, all I need to do is solve for that missing ratio. So let's fill in and see what we get. So a to the n, our 5th term, is 54. That equals our first term, 1 over 24, times r raised to the n minus 1. Well, if n is 5, n minus 1 is 4. And so this is going back to our exponential equations. How are we going to solve this? What do we need to move first? Well, let's deal with that fraction. Again, the 1/24 is just multiplying r to the 4. So let's multiply both sides by 24 to clear that out. So that's going to give us 1296 equals r to the 4th. And then how can we undo that 4th exponent? Well, that's when we're going to just take the 4th root of both sides of the equation. So again, if you're on your graphing calculator, hit math, and then I think it's option 5, but you do need to type the kind of root in first. If you do that on the Desmos calculator, it'll just leave a space for you to, type in the type of root that you want. And when you find your 4th root, you should find that r equals 6. So that's what you're multiplying each step by. So just multiply your first term times 6. So 1/24 times 6 is going to give us 1/4. Times another 6 is going to give us 3/2. Think of it as 6 over 4, because I'm multiplying by 6, 1/4 times 6, and then just reduce that down. And so then if I multiply the top by another 6, well, 3 times 6 is 18. 18 divided by 2 gives me 9. 9 times 6, right back to 54. Okay, I would go ahead, maybe try out number 11 on your own. Again, you're taking the info that we can find out from the list that they gave us, plug it into the formula, solve for the r, and go from there. Go ahead and pause the video and try this one out, and then come back and see how you did. Alrighty, so a sub 1 is our 32. We have 1, 2, 3, 4, 5, 6. So that's a to the 6. So n equals 6. So plugging in 1 equals 32 r raised to the 5th power. Divide both sides by 32. So 1/32 equals r to the 5th. Well, 1 to the 32nd, again, take your 5th root of both sides, and you should find out that you get 1/2. Again, way to think about this too is if you play around with your exponent rules, again, don't forget that, raising 1/2 to multiple powers is really just multiplying the 2 in that denominator. So if our common ratio is 1/2, multiply each term by 1/2 to get the next one. So 32, then 16, then 8, then 4, then 2, then 1.